Right now, if someone asked why a plane's wing generates lift, you'd probably give the textbook answer. It's wrong. A Boeing 747 weighs 412,000 kilograms at takeoff, 65 fully grown African elephants. And the physics actually holding it up isn't what you were taught. So what's actually going on? You've heard it before. The wing is curved on top, flat on the bottom. So air on top travels faster to meet up with the air below at the trailing edge. And that speed difference sucks the wing upward. It's in every textbook. It's also wrong. There's no rule that says the air has to meet up again. It doesn't. The real explanation is simpler and comes down to one principle Newton described in 1687. A wing pushes air downward. The air pushes back, up. That's the entire mechanism. No mystery, no magic. The mystery is what it takes to do that continuously. Thousands of tons of air every second without stalling, without burning absurd amounts of fuel, without tearing the wing apart. Turns out, push air down breaks into 4 separate jobs a wing has to pull off at once. 4 effects working together. Angle of attack. The wing tilts and air striking the underside gets deflected down. Camber. The wing's curve redirects air even at 0 tilt. Circulation. Airflow wraps around the wing, amplifying the pressure difference. Boundary layer. A thin sheet of clinging air that decides whether the whole system keeps working or fails. All 4 have a real cost and a real payoff attached to them, starting with what it actually takes to keep 412,000 kilograms in the air. Lift comes with an unavoidable cost and a hidden reward for flying efficiently. At the wingtip, high-pressure air from below rolls around toward the low pressure above, forming a trailing vortex. That vortex tilts the lift vector backward. Induced drag. It falls sharply with speed, which is why it dominates during slow flight at takeoff and landing. Winglets interrupt that vortex, cutting induced drag by roughly 20%. Worth a 3 to 5% fuel saving on a long-haul flight. Here's the payoff. A 747 at cruise altitude, all 4 engines shut down, glides 15 kilometers forward for every kilometer it falls. A glide ratio of 15 to 1. The same as a hawk soaring on thermals in a machine 400 tons heavier. None of that, the vortices, the winglets, the glide ratio, makes sense yet without knowing where the lift itself actually comes from. So here's the physics, one piece at a time. Bernoulli's principle is real. It's just usually explained backwards. When a fluid speeds up, its pressure drops. That's not the cause of lift. It's a consequence of it. The wing forces air to travel faster over the top. Faster air, lower pressure. Slower air below, higher pressure. The wing sits between the two and gets pushed toward the low side. On a commercial wing at cruise, that pressure difference is around 7,700 pascals. And most of it is concentrated in one place. A suction peak near the leading edge generates 60 to 70% of a wing's total lift. Spread across a 747's 525 square meters of wing, that pressure difference adds up to just over 4 million newtons. Almost exactly enough to keep 412,000 kilograms airborne. Here's what Bernoulli alone doesn't explain. A flat board with no curve at all can generate lift. A wing can fly upside down. The reason is angle of attack. Tilt any surface into oncoming air, even plywood, and the underside deflects air down. Newton's third law pushes it up. At takeoff, wings sit at 8 to 10 degrees angle of attack. At cruise, just 2 to 4, because speed is doing more of the work. The counterintuitive part: angle of attack dominates at low speed. Camber matters more at cruise. Same wing, 2 different mechanisms in different proportions. The most consequential physics on a wing, and the least discussed, happens in a layer just millimeters thick. Right at the surface, air velocity is essentially zero, stuck by viscosity. A few millimeters out, it's back to full speed. That thin transition zone, 10 to 20 millimeters on a commercial wing, is the boundary layer, and it controls everything. As it travels toward the trailing edge, it thickens and can separate entirely. When it does, the smooth pressure distribution collapses. Lift drops. Drag spikes. The wing is stalling. Wing design is really about managing this sheet of air, millimeter by millimeter, across the whole surface. Here's where it gets genuinely strange. A wing doesn't just redirect air. It makes the air rotate around it. The airflow around a wing is straight flow plus a bound vortex, circulation. The Kutta-Joukowski theorem says lift per unit span equals air density times velocity times that circulation. More circulation, more lift. And here's why every wing, from a Cessna to an A380, has a sharp trailing edge. Airflow has to depart it smoothly. The Kutta condition. A blunt edge would create chaotic flow and destroy the circulation entirely. A cruise wing and a takeoff wing aren't the same wing. At cruise, 900 kilometers per hour, high altitude, a small angle of attack generates lift efficiently. At takeoff, 250 to 280 kilometers per hour. The same wing would need such a large angle of attack, it would stall. So the wing changes shape. Slats extend from the leading edge, delaying separation at high angles. Triple-slotted Fowler flaps slide aft from the trailing edge, adding both camber and area. A fully extended flap system boosts maximum lift by 70 to 80%. On a 747, the actuators that do this weigh 3,000 kilograms, more than a family car, just for the system that reshapes the wing. One specific wing, the Boeing 747-400, in production for 54 years, longer than any other wide body ever built. Span, 64.4 meters. Area, 525 square meters. Sweep, 37.5 degrees. Not aesthetic, it delays shock waves at Mach 0.85 cruise. Its supercritical aerofoil spreads the suction peak to cut wave drag. Maximum lift-to-drag ratio, 18 to 1. 18 newtons of lift for every 1 newton of drag. Before it ever carried a passenger, this wing was bent on a test rig to 150% of the worst load it would ever see in flight, and had to survive. In 1989, a Boeing 747-400 flew London to Sydney non-stop. 17,039 kilometers, no refueling. That record stood for 16 years. Commercial jets sweep their wings back 25 to 35 degrees. The reason reveals something fundamental about high-speed air. Near the speed of sound, airflow over the curved upper surface can go supersonic even while the aircraft is still subsonic, forming a shock wave. Drag spikes, lift collapses. A swept wing only feels the airflow component perpendicular to its leading edge. Sweep it 30 degrees and the wing behaves as if flying roughly 13% slower, pushing shock wave formation to a higher real speed. Without it, fuel-efficient cruise at Mach 0.85 doesn't exist. A wing pushes air down. Newton's third law pushes the aircraft up. Bernoulli explains the pressure difference, but doesn't cause it. 7,700 pascals across 525 square meters, enough to hold 412,000 kilograms aloft. A boundary layer 15 millimeters thick, deciding whether the wing flies or stalls. An 18-to-1 lift-to-drag ratio in a machine the weight of 65 elephants. The physics of flight isn't mysterious. It's Newton, Bernoulli, and a century of engineers figuring out exactly how to use them. A wing balances lift and weight every single second it's in the air. Thousands of newtons matched continuously, or the aircraft falls. That same real-time balancing act happens at a continental scale underneath your feet, and it has a limitation that sounds impossible. It can almost never save its own product for later. Why the power grid cannot store electricity. Next on NG Simple. Subscribe to NG Simple so you don't miss it.